Anomaly detection algorithms identify deviations from normal system behavior. In many engineering applications, you may have plenty of data representing normal operation, but only limited examples of anomalies. The Time Series Anomaly Detector app lets you train models that characterize normal system behavior without requiring labeled anomalies. You can interactively train and test anomaly detectors using statistical and AI methods to develop algorithms for various engineering applications without being an AI expert. The Time Series Anomaly Detector app guides you through the anomaly detection workflow shown here. Throughout this workflow, you work with two data sets, one for training and one for testing. The training data represents normal system behavior, while the test data includes some anomalies. The example we're going to demonstrate today uses sensor data obtained from a water treatment system test bench. The training data is normal, and the test data contains a few labeled anomalies. In the first step, you import the training data. You then select and train a detector to characterize normal system behavior. In the next step, you test the trained detector on test data to detect anomalies. You can then apply the trained and tested detector to a new set of data directly in the app or export the trained detector for use on new data. Let's now walk through these steps in the app. We start by importing the training data. The unlabeled training data set contains three signals. We will load all three channels and use the default percentage of data to set aside for validation during training. Once imported, you can visualize the data, normalize it, and inspect one or more channels. In the next step, you can choose from statistical, machine learning, and deep learning methods to train a detector. The All Quick to Train option is a good starting point, allowing you to select detectors that train fast. Selecting a detector displays an overview of the technique, the types of data the method works best with, and tuning tips. Here, the selected deep learning model, DeepEnd, is well suited for our training data, which exhibits short range repeating patterns. After model selection, we can interactively set up the training parameters and, once ready, train the detector. When training completes, the app shows the training results, including validation plots and metrics and the training loss. You can use them to verify that the detector classifies normal behavior data correctly, and if you train multiple detectors, to compare their performance. The anomaly score distribution plot shows that all the data is below the computed threshold. We see that the detector achieved good performance with zero false positive rate, as seen in the validation chart and confusion matrix. However, these results don't reflect how well the model will detect anomalies in practice. To assess that, we need to test the trained detector on data that includes labeled anomalies. For this, we import the test data. After selecting it, we specify the dataset variable with anomaly labels and then import. We then switch the detection data to the labeled test data that we just imported. After configuring detection parameters, we're ready to detect anomalies with the trained DeepEnd detector. Once detection is completed, we can use the detection metrics and plots to evaluate performance. In the anomaly score distribution plot, we see how the threshold separates normal from anomalous behavior in the test data. The detection metrics table contains metrics for assessing the performance of the trained detector. You can refer to this documentation page for interpretation of the evaluation metrics. Here, a high F1 score along with a relatively low false positive rate indicates good performance. Note that typically this is an iterative process, and you may need to tune training and detection parameters until you get acceptable performance. In the time series anomalies plot, intervals highlighted in yellow are labeled anomalies, and red marks detected anomalies. You can zoom on the plot or move the purple vertical line to a specific location to observe the close-up view in this plot. You can also select an anomaly location from this table for a detailed view. The final plot displays anomaly scores relative to the threshold, where peaks exceeding the threshold correspond to the detected anomaly locations in the signal view. Overall, this train detector shows strong performance, detecting most of the labeled anomalies. Once the anomaly detection results meet your performance requirements, you can apply the trained and tested detector to a new data set directly in the app or export the trained detector to integrate into a larger system. In summary, the Time Series Anomaly Detector app lets you interactively train and test anomaly detectors using statistical and AI methods. To get started with the app, download the Time Series Anomaly Detection for MATLAB support package.